Sime. So she's the science leader of the British Antarctic Survey Ice Dynamic and Paleoclimate team. Also leads our Earth System Modelling Group and is science lead of NERC's large international surface fluxes in Antarctica programme. Louise has also been part of the PMIP effort, kind of developing one of our AR7 fast track experiments, looking at the impacts of abrupt sea ice loss. And I think she's going to be discussing that in her presentation today on a sea ice free Arctic at 127K, CMIP6 and beyond. We can see your PowerPoint, it's just not in like full screen. So if you just go to slideshow, up at the top on your PowerPoint.
Louise, you're muted.
Yeah, I can't hear you, Louise. Oh, there we are. That's it. But we still can't hear you.
Okay, does that work now?
Yes.
Okay, so do you see it in presenter view or do you see it on the main screen?
We're seeing it in the full screen at the moment.
Okay, good. All right. Once it goes
Thanks,
into full screen, I can't see the buttons anymore. I can't see anything, so it's good. If it works, that's good. Right, thank you. Yeah, I have to say that was a great seminar. It was also a fantastically good introduction to the Arctic, sea ice in the Arctic. So thank you on two levels, Susanna. Yes, as Eleanor said, there was a suggestion to have a talk on the fast track plans for PMIP. So that's where this talk comes from, and it was titled "The Sea Ice Free Arctic at 127,000 years ago." And as Eleanor said, it's kind of aimed at explaining our thinking for proposing a fast track simulation. Now, can I make anything move forward is a question next. Oh, yeah, that presumably moved a slide, hopefully. Somebody can tell me if it didn't. Good. So Suzanne's already presented a version of this. This is the version from the NOTS paper from 2020. And she's already mentioned that there's a relatively large spread in when the Arctic is projected to become sea ice free under the CMIP6 simulations. And she's also very handily said that while some of that is down to unknowns about the pathways, some of it is also about, I think you termed it as model uncertainties. And I would suggest that we sort of think about it in a sense as model physics. So most of what we know about the Arctic and how we sort of constrain models is based on the observational period from the satellites, which is all well and good. And that's where we obviously have the very best data from. But it's not necessarily sufficient, I would say, to be able to answer some questions about what model physics are important. So that's kind of partly what we'd like to address in the proposition and for the fast track simulation. So to feed into this question of which model simulations we trust in terms of when the Arctic will become sea ice free, and particularly what sort of model physics matter. So we can, as well as the satellite period, we can go further back in time to help evaluate models and sea ice projections. So here you're seeing some data from Greenland ice cores for the last interglacial period. So we have a period in these ice cores of about 7,000 years, from about 127 to about 120,000 years ago, when it does look like the Arctic was significantly warmer than the pre-industrial and indeed during present day as well. So we think it was around about 4 degrees warmer, at least in the summertime, for a prolonged period. In addition, there's been some recent work which suggests that the occurrence of T. quincaloba, which is a sort of open water species, in these cores here, probably in the last interglacial, although it can be hard to date these sediments, also suggests that the Arctic was warm and likely either practically ice-free or near practically ice-free, so around about the 1 million kilometers of sea ice area left. So if we want to set our models up for that time period, then this period 127,000 years ago is really quite convenient, because we think that the ice sheets looked rather like they do in the present day or in pre-industrial. And actually, we know from ice cores that the amount of CO2 in the atmosphere was roughly the same as pre-industrial period. So it was about 275 as opposed to 285 parts per million. So there's not a lot of difference between the pre-industrial and the period 127,000 years ago, which is convenient for setting simulations up. But there is one huge difference, and that is in the insulation forcing. So this plot here on the right is showing you the difference in insulation forcing between the pre-industrial and that period. And what you can see there is that in the periods between about May and July, there's up to about 70 watts per square meter extra incoming solar insolation in that spring period in the high north. So this period was chosen by CMIP4 for CMIP6. So there's been about, depending on how you count them, about 11 to 16 separate CMIP6 models have run already under CMIP6, 127,000 year ago simulation. And all of them are warmer, and some of them do this. So this period, intense summer sunshine, when it's imposed, or springtime sunshine, which is imposed on the UK CMIP6 model, had GEM3, becomes sea ice free in summer. So the top plots there show you the pre-industrial sea ice extent in blue, and the yellow at the top shows you the last interglacial sea ice extent. And you can see it's below 1 million square kilometers for a couple of months of the year. I quite like showing this. I tend to think this is the first and probably only time that we'll get published in a high impact journal with an empty plot being the main result. So basically that is the main result. In September, there's no sea ice, at least in this model. In addition to the evidence from the ice cores, we also have other types of record of temperature change. We have about 21 records. And if you take an average of those for the last interglacial, we think you've got warming and Arctic-wide warming in the summertime of about 3.7 or a core site mean of about 4.5. There's a small difference because there's a bias in where the cores are positioned. Now, if you compare the summertime temperature from the UK HADGEM simulation for 127,000 years ago with these 21 records, you get really quite a good match with the summertime temperatures. So they both show a warming, as I say, of around about 4 degrees, although there are obviously uncertainties in these data. The signal is larger than we have in the present day, but the uncertainties are a bit larger too. So this would match what we're seeing from the marine core data, if that's correctly dated, and it matches what we see in the ice cores and these other cores as well. So we think that's reasonable evidence that that's what the models should be doing, but not all the CMIP6 last interglacial 127K simulators do the same things. This is one of the main things to point out. There's really a big spread. So this is showing the Arctic mean air temperature, and you can see actually HADGEM3, the UK model, is really warm. Almost all of them show warming, but the amount of warming is really variable. However, if you do look at least on the most basic level between the association between the Arctic summer surface air temperature here in the x-axis, it's a mean station location from that 21 set of locations, core locations, and against the sea ice area reduction, then you see there's a really, really strong relationship between those two things. And if we take our core mean value as being correct at about 4.5, altogether those models would also suggest that that 4.5 core site mean warming value would imply you're losing about 4.2 million square kilometers of sea ice, which would put you just on the threshold between it being sort of sea ice free and or below. If you basically have about 1.2 million kilometers left, so that would mean some summers would be effectively sea ice free and some would be just over that threshold. So of the model simulations, of these 12 that we've taken here from relatively independent models, there's 3 of them which are occasionally practically sea ice free below this 1 million square kilometre threshold. And what we think is interesting about this is that the 2 which do a relatively good job for the present day sea ice and which also go sea ice free, both have the same sea ice scheme in them. So both of them have explicit melt ponds. So this is effectively what happens for HADGEM3 and we think CSM2, although we still need to do the analysis to double check this. So once you impose this really strong insulation forcing, you effectively try and spin up your last interglacial simulation, you have a really rapid reduction in the amount of Arctic sea ice. You can see here that it's actually below the 1 million square kilometre line within 4 years of the spin up starting. So we've looked at this in some considerable detail in the last years, and what we think is happening is it's nearly all atmosphere related. So it's not the same mechanisms that Susanna was talking about. Rather, in this case, the intense sunshine here is leading to earlier melt onset on the top of the sea ice, so that you have melt ponds forming. The y-axis in this plot is the melt pond area. That gives you albedo feedback, so the dark pond surfaces. Then you have a faster rate of summertime sea ice melt, and that can lead to a complete summer sea ice loss. And actually, the reason here for the last interglacial 127,000 year simulation, the melt pond area dropping in sort of late June and July is because there's effectively no sea ice left for the ponds to sit on. So that's why you're seeing that shape. So in essence, this is what we think is happening. You're having these type of melt ponds on the surface, but they're happening earlier and they're more influential. So questions. We think that models which simulate a sea ice-free Arctic in summer are probably more accurate because that seems to match most of our evidence better. We don't really entirely know, I would say, whether the explicit melt pond schemes are crucial. They seem to be crucial for the models where we have it sea ice free, but like I say, we only had 16 simulations for this. And we did find out interesting stuff for the near future as well from this. So up until now, I think it wasn't really clear that having an explicit melt pond scheme was particularly important, because if you ran a simulation, at least for the pre-industrial, that's what I'm showing here, with either an implicit, so a green version of the model simulation, or an explicit melt pond scheme, it didn't matter very much. You more or less got the same sort of September sea ice extent. However, what we found while we were doing this and what we've just published is that it really, really does matter whether you have explicit melt ponds once you get to warm climates, either the past, last interglacial warm climate, or also it really matters for the near future as well. So the different versions of this model, HADGEM3 with explicit and implicit melt pond schemes, have really different behavior in the near future. We looked at this in some detail, but for time purposes, and because I'm not the absolute expert on this, I wouldn't say a lot, just that when we've looked at why this occurs, the ponding of water in this scheme on the thinnest ice categories, so categories 1 and 2 seems to be really important. So variations in the amounts of sea ice within the different categories are matters. Okay, so those are the 2 questions we kind of started with. So far, under CMIP6, with our limited number of models which capture what should happen, we think, in the Arctic, it supports relatively early ice-free dates. And we say that because both CSM2 and HADGEM3 have sea ice-free dates under business as usual type scenarios of around about 2040. And in terms of answering the question of which model physics matter, so far, what we've shown is that the melt pond physics really matter, at least for the UK model. However, what we hope is that our new protocol and more simulations for the abrupt Lig 127K fast track will help uncover new insight. So I think it's fairly safe to say that PMIP is quite excited that we've got a fast track simulation, fast track protocol in here. We wrote this this abrupt lig 127K fast track protocol in late 2023, and then we were really pleased that it's been accepted as one of the, I think there's about 28 fast track experiments. So it's this one here. And if this timetable, if groups stick roughly to this, and that what we'd really hope is that more model groups are able to set up this 127K, abrupt 127K simulations sometime from 2025 onwards. And I think if that is possible, then we would be able to see whether more of these models do produce the warm and sea ice free Arctic at 127K. And I certainly think that because of the magnitude of the signal that we're looking for, should help us uncover new insights into models and help us use the past to understand what physics really matters. And that's where I was going to stop.
Thanks very much, Louise. Have we got any questions? Just pop up your hand. We'll give people a couple of minutes to think. Just in terms, obviously the fast track's targeted at the AR7, so it's kind of, you know, with that climate policy and sort of policy making in mind. What do you think the outcomes of this experiment will kind of provide for that international policy making or national policy making?
Ooh, that might be beyond my pay grade. I mean, because none of these models are ever tuned on any form of paleo data, what we are providing is an entirely independent test of whether they work for past large climate changes, and particularly whether they work for warmer than present day climates. And I think for various reasons, the Arctic is a particular target for this. So I think I hope that we can help the community think about which models are more robust for warm periods, and particularly what types of sea ice model physics are more appropriate for that. Beyond that, I think maybe I wouldn't attempt to answer that at the moment.
That was great, thanks, Louise. Fabrice?
Hi, Louise.
Hi, Fabrice.
Nice to see you. I have a bit of a technical question. Okay, so the Global Stocktake 2028 will be in December. The technical meeting prior to that was supposed to be in June, but now UNFCCC officials say they want to push it forward to maybe early 2028, something like that. This means that the IPCC AR7 Working Group 1 report would have to be done by end of 2027. How likely do you think is it going to be that these fast track simulations and the publications will be done in time for such a deadline, if such a deadline would be decided upon? Is that feasible?
I think that's a really interesting question. I mean, to be entirely honest, I haven't so far been involved enough in these discussions to have any strong overview. I know a reasonable amount about goings on with the UK models for this, and difficulties in trying to get models to a point where they're usable, like even for fast. Yeah. So I think I would be very happy if someone else in this room wanted to make comments instead on Fabrice's question.
So from our side, that would be very challenging, because there's this balance between the needs of the global stock take, you know, and the AR7, but then the capacities of the modelling centres being able to bring everything together, you know, the historical forcings, the scenarios, the harmonisation of them, the data request, everything that's needed in terms of the infrastructure to serve the data. And there's somewhat of a limit to how fast that can happen within what is essentially a in-kind operation where there's no sort of structural support as such. I think the deadline, the sort of timelines we will firm up after the IPCC plenary, which is later in July. And hopefully at that point as well, there've been discussions between the IPCC and the UNFCCC as well, and how they plan to kind of interact. So I don't think we can kind of give a definitive answer at the moment. It's we were hoping that in the plenary in January there would be a timeline came out of that, but it didn't. So it's kind of delayed that firm planning, unfortunately.
Yes, thank you. Yes, exactly. In July there will be the discussion. So it's kind of a chicken and the egg thing that the IPCC session wants a firm answer from CMIP, and CMIP cannot give us a firm answer until the decision is taken. So it goes round and round. But yeah, thank you for this. So basically the idea here would be it's kind of unlikely that there will be a lot of results before end of 2027 then.
I mean, the aim currently is that the simulations will start springtime next year, that the forcings will be available early next year, and then historicals could start in the springtime. So some may be ready, but it's not perhaps going to be a full enough ensemble by that deadline, because there also needs to be the time for the papers to be written for an IPCC. Yes. So there's a limit to how fast people can write papers and get them submitted and reviewed and everything. So yeah, we also have to see what there's obviously a huge amount of CMIP6 data as well that's there. So it's not like there is no analysis or data available. We have to do the best with what is available, I think.
Thank you.
Okay, so we've got some comments from Christian in the chat.
I was going to say that's not technically a question, but it's a very good point from Christian. Is that it whilst for the protocol, we've suggested for fast track that we would like a minimum of 100 years because we expect very fast responses on the sea ice to the insulation forcing. What he's suggesting is that if any group would be prepared to run their abrupt 127K simulation for longer, then it would also tick off all the requirements for a fuller length, more fully spun up last interglacial simulation as well. Good point, Christian.
You might need to do a bit of a sales pitch to the centres maybe at some point. In the spirit of electioneering that there is currently in many countries.
I was going to say, I'm sure Christian and I and many others in PMIP would be very happy to do some pitching to other centres indeed.
Yeah, well, we'll probably look to try and set up an opportunity for the MIPS and modelling centres to kind of interact and have, potentially sort of pitches, and for the modelling centres to find out more about the experiments as well.